Kwame is investigating a possible relationship between average March temperature, T degrees Celsius, and tea yield, Y kilograms per hectare, for tea grown in a particular location. He uses 30 years of past data to produce the following summary statistics for a linear regression model, with tea yield as the dependent variable, which means that we're having the tea yield on the y-axis and the temperature in this direction. And the tea yield is y, so we'll just change that to a y. So we've got a y against t graph like so. We've got the following information: residual sum of squares, STT, SYY, and for the least squares regression line, we're told the gradient is 45.5 and the y-intercept is 2080. We want to use the regression model to predict the tea yield for an average March temperature of 20 degrees Celsius. So the graph is going to look something like that, with the gradient of 45.5 and the intercept here at 2080. And all we want to know is the value here when t is 20. So that's just going to be, so this is part A, 20 times 45.5, add 2080. And that gives us 2,990, and the units there would be kilograms per hectare. He also produces the following residual plot for the data. Explain what you understand by the term residual. So a residual is the difference between the observed value and the predicted value. I always use the mnemonic AMP, which is actual minus predicted. Then in part C, we want to calculate the product moment correlation coefficient between T and Y. Now, delving into the formula booklet, I found this formula that should help. We've got the residual sum of squares here. And if we ignore the middle bit, because we don't actually know SXY, so if we ignore this bit, we do know this because the R is the correlation coefficient that we're trying to find. So it's just a case of substituting in values given in the question. The RSS, so this, let's go back to it as part C. The RSS is 1666567, and the SYY is 1774155, and then we've got the 1 minus r squared just here. And it's fairly straightforward to solve this. So we're going to get 1 minus r squared is going to be 1666567 divided by 1774155. So r squared is going to be 1, take away that division there, and just evaluate and square root, and we get r is equal to 0.246, giving that to 3 decimal places there. In part D, we're asked to explain why the linear model may not be a good fit for the data, firstly with reference to our answer to part C, which is this. This is quite a low correlation coefficient, and that implies poor linear correlation. So that would be a reason why that may not be a good fit with regard to that answer. If we look at the residual plot, when we're going to use a linear model, we'd like to see a random distribution of the residuals. Now, that may be true up to about here on the graph, if we look at the values over here for less than 20. But as soon as you look at the values for more than 20, you can see that there appears to be a pattern to them. And therefore, it seems that the model wouldn't be good for values above 20 degrees. Kwame also collects data on total March rainfall, W millimeters, for each of the 30 years. For a linear regression model of W on T, the following summary statistic is found. Residual sum of squares, RSS, is 86,754. He concludes that since this model has a smaller RSS, there must be a stronger linear relationship between W and T than between Y and T, where, as we saw from above, RSS was this much bigger number. State, giving a reason, whether or not you agree with the reasoning that led to his conclusion. Well, quite simply, no, but you have to have a reason. And the reason is we're measuring something completely different. In the first place, we had the T yield against the temperature, and now instead we're looking at rainfall. And so that's going to be something completely different with completely different units. So you can't just compare these values because, of course, other values that feed into these will also change.